Lesson 2 today, polar graphs and equations. An equation whose variables are polar coordinates is called a polar equation. The graph of a polar equation consists of all the points whose polar coordinates satisfy the equation. We're going to look first at a plot pointing method where we can take our calculator and graph 4 sine theta. You notice it's a circle. And then I can evaluate for our table values. So the radius is 0, means we're at the pole or the origin, so we're at 0. When the radius is pi over 6, I could do that in my head, should be a half. So that's 2. 4 is pi divided by 6. Half of 4 is 2. And at pi over 3, so on and so forth. So we have 2 radical 3, which is 3.46. And at pi over 2, it's going to be 4. And then we're going to go backwards with symmetry. This would be 3.46. This would be 2. And when we get to pi, it's going to be 0. Okay, so if a polar equation involves only r equals a sine theta or r equals a cosine theta, your graph is going to be a circle. And we can be able to describe the direction after a little bit of experience. So this one we saw it was at 0, and then at 4 the center was at 2, and at 2 we had pi over 6 and 5 pi over 6, and we had 3.46. So 1, 2, 3.46 at the 60 degrees. So we've got a circle that's looking similar to that. So when I have a positive cosine, r equals positive cosine, or negative cosine, we're going to find out that that has x-axis symmetry. Whoop. And if it's a positive a, it's going to lean to the right, or the circle will go to the right. If we have a negative a, our circle will be on the left of the x-axis. And if we have positive or negative a sine theta, as in this case we had 4 sine theta, you'll see we have y-axis symmetry, like we saw in the example. And if you had a positive a, the circle would be positioned on the y-axis or up. If we had a negative a, the circle would be positioned on the y-axis or down below the x-axis. So those are the characteristics if we just have a r sine theta. So 4 cosine, it's a positive. It would be 4 cosine would be a circle on this side. And negative 2 cosine would be a smaller circle whose radius is 2 on the left side. 2 sine theta would be the same size as the 2 cosine theta, but it would be up. And negative 3 sine theta would be a circle positioned down. So these are the pattern recognitions for those particular basic polar curves. Now, the test for symmetry, if you replace theta, I'm going to say verbally, we're going to replace theta by theta minus pi, then the symmetry would be y-axis symmetry. So you can also say that as it's symmetric about pi over 2. For the second test, if we replace theta with the opposite of theta, then we would have x-axis symmetry. And that's the same as saying we had polar axis symmetry. And then the last one, verbally, if you replace r by the opposite of r, you're going to find that you have origin symmetry, or you can also call that symmetry about the pole. Okay? So those 3 tests are sufficient to guarantee symmetry, but they're not necessary. That is, if a graph fails a symmetry test, it doesn't mean it's not symmetric. But if it passes the test, it must be symmetric. So when we have r equals f of the sine of theta, it's symmetric with respect to, this should be the x-axis. This is backwards. And if we have g cosine of theta, then cosine is symmetric with respect to the y-axis. I take that back. This is right. If we have sine of theta, we just graph that. If you have r sine of theta or 4 sine of theta, it's symmetric with respect to the y-axis. And if you have cosine of theta, that would be symmetric with respect to the x-axis. So there are certain types of polar curves that happen. The first one we're going to look at is called a cardioid. It has a little heart shape. It's kind of dimpled in like that. And we want to look at some patterns here. So this one has symmetry about the polar axis, which is our x-axis here, polar axis symmetry. And the ratio, we're looking at these numbers, this A and this B number. So the ratio of A to B is 1. And it's a positive cosine. Since it's 4, 2 plus 2, it's positive cosine, 2 cosine. So that's how I know it goes to the right. That's one of the patterns. And there's going to be a little trick to graphing. So if we take the A and B value and you add them together and subtract them from each other, they give us a clue about how to graph if you don't have a calculator. So if I add the A and B and subtract the A and B, adding them I get 4. 2 minus 2 gives me 0. The A value is 2. So the A value tells me to go up and down, and the sum of the two tells me to go to the right because it's positive. So I know my graph is going to be centered to the right. So if you look at the graph carefully, this tells me I've got a plot here, and I'm going 4 to the right because it's a positive 2 on the cosine. But notice here, the A is, this first A is 2, so I know that I go up and down 2. And that holds on this example as well. So this first 2, since it's a negative sign, I know negative sign means it's got to go down. And if we add the 2 together, we're going to get 4, 2 plus 2. We're going to get down 4. But this first 2 tells me to put a point here and a point here to the right and the left. So this A value tells me to go that way, where this A value, because it was cosine, told me to go up and down. And this one, because it was sine, told me to go right and left. Because the symmetry here is on the y-axis, or we could say theta equals pi over 2. So I still have the same ratio. A over B is 2 over 2, so that's 1. And the function was sine, and it was negative sine. So that told me that my curve had to be going down or below the x-axis. And when we added and subtracted the two values, those were my clues of where the points went. So if the sign is a negative and it's down, then the sum of the two tells me to go down. This one told me to have it 0. This other a, the a value, the first value, told me to go right and left because the function's going down, so this is the opposite direction. That gives you a real quick way to get a few points, knowing that the pattern tells me it's a cardioid, and I know how it looks, and it's got that little dimple in there. Gives us a clue. We'll describe the patterns here in a minute. Let's do 2 more. So this one is kind of caved in a little bit, but that's because our ratio is getting larger. So the symmetry, again, is on the polar axis. It's symmetric along the x-axis or the polar axis. This one, the symmetry, is on the y-axis or pi over 2. This one, our ratio a over b is bigger than 1. And it's a positive cosine. So positive cosine tells us it's going to go to the right. And then a minus b is 3 minus 2. A plus b is 3 plus 2. And then the a value is 3. So how can we say this? A plus b is 5. That goes to the right. A minus b is 1. That goes to the left. See, the other ones on the other page had a 0, so that just stayed at the origin, where this actually moved 5 to the right and 1 to the left. And the a value of 3 tells us where 2 more points are, at 0, 3, and at 0, negative 3. And it's just kind of a dimpled in cardioid. This one, our ratio is even bigger. A over b is 5 over 2. So it's almost circular. Not quite, but almost. And because the sign is a negative sign, we know that it's got to be positioned downward. So the a minus b is 7. So we go 7 down. And the a plus b is 3. That's 3 up. So 3 up, 7 down. And the a value is 5. On the opposing axis, it's going to be 5. So almost circular. And then I guess I need a page to say what the patterns are. So we could say at the beginning, if the pattern, absolute value of the pattern, if that's a 1, we know it's a cardioid. If we're in between 1 and 2, those are called a dimpled cardioid. So the dimpled cardioid was example C. And if the ratio is 2 or bigger, which was like example D, that's known as a convex Limacon. That was letter D. And what did we find out? If we did A minus B and A plus B, those give us axis values in the direction. And the A number is also an axis value. So this one would go by whether it was sine or cosine, and this would be the opposite axis. So if it was cosine, this would be x-axis. This would be y value. If it was a sine function, these would be y axes, and this would be the x-axis. So just a little ability to graph without making a table of values. So here we're going to look at the Limacon, and that should have a little accent down there. So on the Limacon, it makes a loop, and you can tell by looking, this has polar axis symmetry. This one has y-axis symmetry or pi over 2 symmetry. This one, the ratio is 1/2. A over b is 1/2. That's less than 1. This one also, A over B is 1/2. That's less than 1. So without writing too much, A minus B, so 1 minus 2 minus -2 is 3. 1 minus -2 is 3. So this is negative cosine. It's going to the left. We'd go 3. And then 1 plus 2, or 1 plus -2, is -1. So that's going to go to the left as well, -1. See, -1. This is 3. And they're going left because it's negative cosine. And the A value is 1, so we would have a point there and a point there. And it would start here and spin around to make that inner loop. In example B, we have 1 plus 2, that's 3, and it's a positive sign, so we're going up, 3 up, and 1 minus 2 is -1, so it's going up again. That's the inner loop, and the A value is 1, so we have those going there, okay? And then on the C and the D, 1 plus 2 cosine has polar axis symmetry. Polar axis. 1 minus 2 sine, that has theta equals pi over 2 symmetry. The ratio is 1/2. Ratio is 1/2. Positive cosine goes to the right. And 1 minus 2 is -1. And 1 plus 2 is 3, both going to the right, and the A value goes up of 1. And this one's the same thing. We're going to go 3 down, and 1 right and 1 left based on the A value. So what things did we see as far as patterns go? We're going to answer this to explain the pattern. If the absolute value of the ratio is less than 1, it's going to create an inner loop, and that's called an inner loop limacon. We saw in the previous examples, if the A over B is exactly 1, it creates a cardioid. And if the A over B ratio is greater than 1, it's going to either be dimpled, or convex, cardioid or limacon. Now we can get really fancy with some rose curves. So when you have n greater than or equal to 2, if n is an odd number, that's going to tell us how many petals we have. But if n is an even number, we have to multiply, we have to double that to get the number of petals. So in this case, n is odd, or n is 3, and we have 3 petals. So it's odd. And we have polar axis symmetry. In this case, we have pi over 2 symmetry, and the n value is odd, so we have 5 petals in that case. Now, how do we know where the petals go? Well, if you take 360 degrees for one complete revolution, and we divide by the number of petals, that tells us every 120 degrees we'll have a petal. So starting with our polar axis symmetry, then 120 degrees away from that, and then again at 240 degrees, and then back to 360. So our A value is 3. That tells us how long the petal is. Whoop, was our A? No, our A value was 2 in this case. I'm looking at that 3. The A value is 2, so our petals are 2 units long, or the radius is 2. And the petal length, that tells us on the x-axis. Okay, this one, because it's sine, we have our petal length on the y-axis, and 360 divided by 5 tells us every 72 degrees we're going to have a new petal. So we would start here, and then 72 degrees away, and 72 degrees away, and 72 degrees, and 72 degrees, until we came back around to our pi over 2 symmetry line, right? This one had polar axis symmetry. So we started here and went 120, 120, and so on. So our A value is 3, and the petal length was on the y-axis. That was our first petal right here at 72. Okay. In this one, we have an N value that's 4. So 4 times 2 means we're going to get an even N value, and 4 times 2 means we have 8 petals. So 360 degrees divided up evenly among 8 petals is every 45 degrees, and the petal length is 3. So since we're cosine, our petal axis is going to start on the polar axis, but it also has pole symmetry since it's reflected across the pole. So every 45 degrees, there, here, 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 here. So it's symmetric about the pole, and it's symmetric about theta. It's also symmetric about the y-axis. So this has symmetry on all 3 points: the pole, the polar axis, and the line theta equals pi over 2. In example D, again, our N value is an even number, and I believe we have the same all 3 symmetries. We have symmetry about the pole, we have symmetry on the polar axis, and we have symmetry about the y-axis at pi over 2. So our petals, we have an even N value, and 2 times 2 is going to give us 4 petals, and 360 divided by 4 means every 90 degrees. And since it's at, it's a 2 theta, our angle. So 2 theta is 90 degrees. That means our theta is every 45 degrees, right? So at 45 degrees, starting here, we would have 45 degrees, 45 degrees, 45 degrees, 45 degrees. Okay? So rose curves have to pay attention to even and odd to know how many petals if you're identifying without a calculator. Now this one is interesting. We want to find the zeros where r squared equals 16 times sine of 2 theta. Now this is going to be called a lemniscate. So we want to solve for r, which means we're going to take the square root of 16 sine 2 theta. And we can take the square root of 16, that's 4, and 4 sine 2 theta. And this figure is going to be called a lemniscate, Lemniscate, and it's going to look like a figure 8. Figure 8. Let's see if I have it drawn already. Nope. Okay, we'll set that up. So one thing we're going to want to do is to make our table. We're going to make a table. And we're going to make the table set to pi over 12. Pi over 12. So let's set that up with our calculator. So here's a picture of my figure 8 or lemniscate. And since I have the TI Inspire, I'm able to just evaluate that. So we've got a figure 8 that's going to go, well, let's first of all make the table. So I can go over to the scratch pad, and when R is 0, we're going to look at our theta. So we've got when theta is 0, and we're going to look at pi over 12, pi over 4, 5 pi over 12, and pi over 2 using our calculator. So I want to pull up the function, and I want to know when theta is 0, we got 0. When we have pi over 12, we have 2.82. Pi over 4 is 4. And 5 pi over 12, 5 pi divided by 12 is 2.83 again, and then at pi over 2 it should be undefined. Nope, it's at 0. Okay. So filling in that table, we have 0 and either plus or minus 2.83, plus or minus 4, plus or minus 2.83, and then back to 0. So at 0, we're at 0. At pi over 12, that's 15 degrees. We're at 2.83. And we're also at 2.83. We got 4 at pi over 4. So it's going to go around like that. Come back around here. And then do the same thing again at 5 pi over 12. We're at 2.83. And we're at 4. It's going to come around this way. And back to 0. Okay? So we have 2.83 at pi over 12. We have down here, we have negative 2.83 at pi over 12. So remember how we were doing our positive and negative angles in the first lesson. If you go out 2.83 and down, that's a pi over 12 angle. If you go right 2.83 for the radius and up pi over 12, that's still a positive angle. So back to our analysis here. This is about 0.2618 is pi over 12. And the change in the degree, that's 15 degrees, is what we did with the table. So the zeros occur at 0 and pi over 2 and pi. I didn't put pi on the table. And we had symmetry. We had symmetry on the pole. And we could see that from our table because 2.83 and pi over 12 was either positive or negative. So we had that symmetry test. And the maximum value happened at 45 degrees, where we went out either 4 positive or 4 negative. So that's called a figure 8 or a lemniscate. And if we use a calculator to complete the table, for the sake of saving time, our function is r equals e to the theta over 4. I've already pre-done this. I get 308 and 0.456 and 0.675 and 0.822. At 0 we had 1. and 1.48, 2.19, and 3.25. So we're going to want to graph that. This is going to create a logarithmic spiral. And it's going to go at 3 pi over 2, we're at 3.308. 0, we got 1. And this is 1 point. This is 2.4, almost 5. So our spiral goes around like such. Now here's what happens if I had my calculator. You can do this and you can double check. Notice that when r is positive for all theta, so as theta goes to negative infinity, this should be negative infinity. Well, we can do it this way. We'll do, as theta goes to infinity, r goes to infinity. But as theta goes to negative infinity, r heads towards 0. Is there any symmetry of this polar graph? Can you explain why? Well, there's no number theta where r equals 0. We don't have any value of theta where we can get r equals 0. So the graph won't pass through the pole. And we could say spirals. It spirals infinitely toward the pole and away from the pole. So the graph spirals infinitely. Whoop, I'm going to write spirals again. The graph spirals infinitely toward the pole and away from the pole. Okay, and that's the end of our lesson on graphing. The next lesson will go into more graphs in a little more detail. See you next time.